All right, so we're going to take a look at 4.3 notes where we are working on different strategies to graph functions. And sometimes you'll hear this reference as curve sketching because we're really going to be making sketches of functions rather than super precise graphs. And we'll be using a lot of calculus in order to do this. So we'll be looking at the relationship between the first and second derivatives and what a graph should look like with different characteristics. Now, some of the things that we'll be specifically looking for, we are going to want to know, are there any relative or local extrema for the curve? Are there any points of inflection and where are they at? Is there a y-intercept? Where are the x-intercepts at? And if it happens to be a rational function, where are any horizontal and vertical asymptotes? Now, I'll be very honest with you. Number one, I would not use calculus to do. I just wouldn't. Rational functions are actually pretty easy to graph with the tools that you guys already have learned in previous math classes. Now, you may have forgotten some of those tools, so I'm going to run through this with you, but when we're talking about curve sketching with rational functions, very rarely is the calculus super helpful. So I'm actually going to sketch this without the calculus, just by using some of the things we learned in Algebra 2. And then we'll take a look at what's happening with the calculus in order to just compare, and hopefully you'll see how it fits together, but how in this case it just may not be super useful. So we know that in a rational function, if there's a domain restriction on the denominator and that domain restriction is not repeated on the numerator, that would indicate a vertical asymptote. So we have a vertical asymptote here at x is equal to -2. For our horizontal asymptotes, if there is one, you can determine where that's at by comparing the degree of the numerator and the denominator. And in this instance, the numerator and the denominator have the same degree, and so the ratio of the leading coefficients will tell you where the horizontal asymptote is at. In this case, it's 1/1. So we have a horizontal asymptote at the line y is equal to 1. These curves will never cross a vertical asymptote. Very rarely they will cross a horizontal, sometimes in the interior region, but never on the ends. But this one is a very straightforward one and doesn't actually cross. If I pick a point, maybe on either side of my rational, of my vertical asymptote, I can get a nice little sketch. I'll pick an easy point like -1. If I plug in a -1 as an x value here, on the numerator I'd get -4. On the denominator I would get +1. And so I would have the ordered pair -1, -4. And so if I fit this curve to my vertical and horizontal asymptotes, it would look something like that. Now for most rational functions, the other portion would then, if one portion is below the horizontal asymptote, the other is typically above, unless we have a numerator or denominator where things are squared, because then we don't see the sign change. But if I just want to check, I'll pick an input on the other side of my vertical asymptote. So if we do -3, I get -6 over -1, which is +6. And as anticipated, it would look something like this. And this is actually a pretty good graph. I'm pretty happy with this graph. I don't really need much more than this. Really, I'm fine with this one. If I wanted to, I could see where the x-intercept is at. My graph's not super accurate, but the x-intercept according to the numerator here would be at 3. So my graph maybe looks a little bit more like this. If I wanted to find my y-intercept here, I could put an input of 0, and the y-intercept would be at -1.5. If I just felt like, gosh, I need a slightly more accurate graph. So how does the calculus fit into all of this? It does, but like I said before, it's just not super useful in this particular problem. But I'm going to go ahead and show you what the calculus actually does look like. I'm going to look at the first derivative here of this function. And in order to find the first derivative, I'm going to use the quotient rule. So the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. You might have heard the saying low d high minus high d low over low low, or low squared. And what I want to do is I want to simplify this expression and set it equal to 0. I'm sure you can handle the simplification on your own, so I'm going to go and not spend time on how we got to this. And then I'm going to look for any critical values. Now, critical values would be where the first derivative is equal to 0, which would occur on the numerator, but there's no input for x. This numerator is 5 only, never 0. Or where the denominator would equal 0, because that would show us the spot where the derivative is undefined. And so the derivative is undefined at an x value of -2, and that is a critical value. So something interesting is happening at -2. As a reminder, a critical value is when we have something, a point of interest. It might be a relative extrema. In this case, it is not a relative extrema. It is a vertical asymptote. So my first derivative really didn't tell me anything new other than, hey, something interesting is happening there at the -2. If I then do the second derivative might be easier if I rewrite the first derivative with a negative power and avoid the quotient rule. If I then do the second derivative, I'll use the power rule followed by the chain rule, which in this case is just multiplying by 1. So I'd have -10 over x plus 2 quantity cubed. Now again, our second derivative is going to be particularly useful for finding possible points of inflection. There are only possible points of inflection until we check for a sign change. And so for the second derivative, the possible points of inflection could occur where the second derivative is equal to 0, which is not possible in this instance because there is no variable in my numerator, and the numerator would only ever equal -10. Or where the second derivative is undefined, which would occur when the denominator is equal to -2. Well, that's interesting. -2 is a critical value, and it's also a possible point of inflection where we might see a concavity change. But we also know it's a vertical asymptote. But if you think about what's happening with this graph, I'm concave up to the left of -2, of x equals -2, and I'm concave down after that. So we could kind of think of this as a point of inflection, except for points of inflection are points. They are not discontinuities. They cannot be at discontinuities. So it actually will not be a point of inflection, even though the reason the second derivative is drawing our attention to it is because it's a place where the sign of the second derivative could change, and in fact it does. Now sometimes it's helpful to make a little table, and this is important. College Board readers will not examine your tables when you're looking at the signs of the first and second derivatives. That doesn't mean the tables aren't useful. Oh my gosh, they totally can be. However, what you need to understand is they're useful for you. They're not useful to convince the reader of anything. They are useful for you to help you then draw conclusions, and then you could then take those conclusions and express them in words to the reader. Well, if I look at my first derivative over my intervals that are split up by my critical value, and I'm going to split up at that possible point of inflection. In this case, they happen to be the same. Basically, what ends up happening is that I get a +5 divided by something positive. And no matter what happens, I'm always going to get a positive output for the first derivative. And so what that tells me is my original function, f, will always be increasing as I go from left to right. In fact, if you look at our picture, you can see, oh yeah, that's absolutely true. This graph is always increasing, except for at my vertical asymptote at my point of discontinuity when x is equal to -2. If I look at the second derivative, I have a negative, and then I have an odd power on the denominator, so this sign will change. If I pick something smaller than -2, I'm going to get a negative on the denominator. When I cube that, that's still a negative. I'll have a negative divided by negative, which is a positive. And when the second derivative is a positive, that tells me that this function will be concave up. When I pick something larger than -2, I will get a negative over a positive, which will divide out for it to be a negative, and my function f will be concave down. So, I mean, my calculus does actually fit the picture, and I guess if I didn't want to test some points, I could see the concavity. I could say, oh, it's increasing and concave up. to the left of x equals negative 2, and it's increasing in concave down to the right of x equals negative 2, and we could find that helpful. By the way, increasing in concave up is the right side of the concave up symbol. It's this. And you can see that's basically how it looks. Increasing in concave down is this part. And you can see that's how it looks. And this is basically how our graph looks with like that vertical asymptote in between them. We just don't have the right heights. So did the calculus fail? No. The calculus did match the picture. But my gosh, what a lot of work for something that we already had. It just verified what I already knew, and it really is non-essential. When you guys see rational functions,